Let's look at a principle called LeChatlier's principle. LeChatelier got the Nobel Prize in 1888 for this sentence: in a system at equilibrium, if a stress in concentration, temperature, or pressure occurs, the equilibrium shifts to relieve the stress. A new equilibrium is established. So we can add substances to our reaction, our equilibrium reaction, and we can change so that instead of reactants being favored, then products can be favored. And so we can do this by changing concentration or the temperature or pressure. You can only influence gases and solutions, never solids and liquids. So remember, when you're writing equilibrium constant expressions, you leave the solid and the liquid out. So if I were to add more water or add more solid, that would not change my equilibrium. Only if I were to add different concentrations of aqueous solutions or gases, or change the temperature or the pressure, that is what would change the equilibrium. Now, in order to influence equilibrium, it first needs to be in equilibrium. So as soon as I've established equilibrium, I can then stress out my chemical system by adding products or adding reactants, or by changing the temperature or the pressure. And you should remember this saying: add away, take towards. So that means if I add something to one side, it will shift it towards the other side. If I add a product, it will shift it towards reactants. And if I remove a product, that will shift it towards the product side. So take towards. And take means that you remove it. And you remove it by binding it up in some sort of chemical reaction, is how you would remove it. So again, add away, take towards. It's a shift away from the side added or toward the side removed. So let's look at this chemical system. So we have reactants, we have products, they're all gases. And this right here is very important. This says that my delta H, or my heat, is less than 0. So this means that this is an exothermic reaction. I actually can write heat as part of the reaction, and it's going to be part of the product side because heat is made and it is released. So it's a product. So let's say this is at equilibrium and I add more of component A. Well, what that is going to do is cause more collisions between A and B, and so you are going to get an overall shift towards the reactants. So it's going to increase on this side, and this side is going to decrease, and overall it's going to shift away. So add away. Let's do the next one. Again, I'm adding a reactant, so that is going to cause more collisions between A and B because there's so much more B that A is just going to run into more B, and so that is going to cause it to react and have more products of C and D. Now, what about heat? Well, heat is a product, and so I also can see an increase in heat in both of these if I add a reactant. Now let's see what happens when we add a product. Adding a lot of C into my reaction vessel, that will cause more reactions between C and D. So I'm going to have a decrease in D and an increase in my reactants. And this will also decrease the heat. So adding to one side shifts it away. So I'm going to have more reactants. The same thing happens if I add more D. If I add more D to my vessel, then C can't help but run into D. And so I am going to have more collisions, and that is going to cause a general shift over to the reactant side. And the same thing happens with the heat. Because heat is on the product side, that will decrease too. So adding a reactant shifts it towards the product. Adding a product shifts it towards the reactant. Let's see what happens if I remove something. So let's say I add a chemical that's going to bind up all the A. Well, now B has nothing to collide with, and so that forward reaction is not going to happen. But the reverse reaction keeps happening. And so as a result, you are going to see a general increase towards the reactant side. So this means I'll have a decrease in C and D and an increase in my reactants. And let's see what happens if we remove from the other side. So if I remove a product, then that is going to shift it towards the product side because I'm going to bind up D, so C and D can't react, but A and B still can. And so you are going to see an overall shift towards that product side. And I like to draw a little line here just so that I can keep it separate. Now, I didn't put heat on the previous one, so let me go back and do that. But we do have an increase in heat on this one that we just did. And when I remove reactant, that will also cause less heat to come out. Now let's look at pressure. So pressure is something a little bit different. When we look at pressure, we're going to look at the number of moles. And what I mean by looking at the number of moles is I'm looking at the 1 to 2 to 1 to 3 ratio. So I see that overall on my reactant side, I have 3 moles. And on my product side, I have 4. So when I increase the pressure, that means that my volume goes down. If my volume goes down, there's less of a space. And because there's less of a space, then the shift is going to go towards the side with the fewer moles. And in this case, the fewer sided moles, that would be the reactant side. So on this one, I'm going to get an increase. If I increase the pressure, I'm going to get more reactants form. So to relieve the pressure, it will go towards the side that there's fewer number of moles, so therefore fewer number of particles, and that will decrease the collisions a little bit. Just it gives it more room by shifting towards the reactant side. Now if I decrease the pressure, that means that my volume goes up, so now I have more room. So it's going to shift towards the side with more moles. So in this one, that means it's going to shift towards the product side. And it's just different depending on the ratios. So maybe decreasing the pressure, I have more moles on my reactant side. So then it would shift towards that side. But in this example, I do have more moles on the product side, so it will shift towards that side, so it will fill the space more. Now, adding a solid or liquid. If you add a solid or liquid, nothing happens. Remember that solids and liquids are not put in equilibrium constant expressions. They don't change the equilibrium because you can't change the concentration or the density of your liquid or your solid. What about adding noble gas X? Well, if you don't see noble gas X in the equation, then it's also going to do nothing. Only the things that are at equilibrium participate, and noble gas X is not in the equation, so it's not going to do anything. What if I add heat? So if you add heat, because heat in this case is a product, then you are going to add to that side and it will shift it away. So I'm going to shift and have more reactants. If you change the temperature, you will change the value of your equilibrium constant. And the next one, changing the volume. Well, refer back to the pressure. So if you change the volume, that means you're changing the pressure. So you want to follow those rules. So increasing the pressure would decrease the volume, so therefore shift towards the side with fewer moles. And vice versa. Adding a catalyst, all this does is you get to equilibrium faster. So it won't affect any shifts. You'll just get to whatever the equilibrium is faster. Here's a diagram that's showing that if you increase the pressure, you decrease the volume. So this is making it so that there's a smaller area, so it will shift towards the side that has fewer number of moles. So in this case, it shifts towards the right because I have 2 moles on that side, and on the reactant side, I have 4. And just the opposite happens if I decrease the pressure. If I decrease the pressure, that means I have a larger volume of container, and so it'll shift toward the side that has more moles so it can fill that container. So in this case, again, it will shift towards the reactants because there's 4 to 2 moles. So see if you can answer these questions. Go ahead and stop the video and then we'll come back and do the answers. True or false, in a reversible reaction, if the reverse reaction occurs more rapidly than the forward reaction, there will be more reactant than product. And the answer to that is true. Because it's easier to do the reverse reaction, you are going to end up with more reactant. And then in question 2, adding more ammonia would shift the equilibrium what direction? So if I add ammonia here, I remember add away. it's going to shift towards the reactant side. So I'm going to have an increase in my reactants and a decrease in heat. These are some demonstrations that we will do in class. I will try to link some YouTube videos after this. But we have colorless versus dark brown gas at equilibrium. So it's just a brownish color. And I have heat on the reactant side. So this means this is an endothermic reaction. My delta H would be positive, so it would be bigger than 0. And heat is just one of the reactants. So if I add heat, so I would put it into some hot water, you are going to see add away occur. So I'm going to see an increase in the dark brown and a decrease in the colorless. If I remove heat, and I do that by putting it in some ice water, that is going to shift the reaction towards the reactant side. So take towards. So take it away from the reactants, it's going to shift towards. So take towards. And I will have it turn more colorless and less of that dark brown. This second system, this is the chromate dichromate. Chromate is more yellow colored, dichromate ion is more orangey colored, and I can use an acid and a base to control what's going on. So if I add more acid, so this H plus, this is my acid, then that's adding hydrogen ion. So remember, add away. So I would predict that it would become more orange, and that's exactly what happens. If I take and add NaOH, then what that does is that makes a reaction where it takes the hydrogen ion and it removes it. I'm making water. So I'm removing my hydrogen ion, and so I know the pattern for removal is take towards. So I am going to see this get more yellow when I remove that hydrogen ion. Notice I didn't put anything down under the water, and that's because this water is a liquid, and so I am not influencing the concentration of the water at all, so I can't change the density. What would happen if you're at equilibrium and then you add something? So that's LeChatlier's principle. This is a diagram that shows adding a reactant. So I have my initial equilibrium. I know I'm at equilibrium because my concentrations are staying the same in all three of them. But then here I'm adding my hydrogen. So I add it on the reactant side. And so let's look and see what happens. We see that equilibrium is reestablished. And this time we see a shift in more of the ammonia. And we see that we have less of the hydrogen. So this chart is showing LeChatlier's principle. In the next couple of slides, I want to talk about an application of LeChatlier's principle and how it changed our world. So in the 1800s, fertilizer was very difficult to come by, and the U.S. population was increasing, and the farmers needed to produce more and more, and it was really hard to get nitrogen fertilizer. Farmers mostly got their fertilizer from animal products, so dung from horses or cows, or they would get bones from a slaughterhouse or blood from a slaughterhouse. This right here is New York City, and look at all that horse manure piled up in the streets. They would have to come to the streets of New York City. People would come and clear the roads every single night. They would toil all night to remove all the manure from all the millions of horses that were in New York City in the 1800s. And then they would take that manure and distribute it to the farms that were surrounding New York City. So quite an undertaking there. Other ways that they could get nitrogen fertilizer is through dead fish. And then this one's quite unique. They would harvest it from these islands that were in a rain shadow. So this is basically an island of bird guano. Here's a real picture of it. It's hundreds of feet high. So the birds would come and roost on these islands and raise their young and do their business with their guano. And that guano just piled up because rain never came. And so you can see people in this picture down here harvesting the bird guano, and they put it in ships and ship it away and then distribute it to farmland. So in early 1900s, the German government, they would have to get their nitrogen fertilizer from Argentina. And when that supply line dried up because of politics, the German government turned towards its scientists and said, is there any way that you can get nitrogen to use for fertilizer? And so this is a picture here of the German scientist Fritz Haber, and this is his famous equation. He took nitrogen from the air, which we have an abundant supply of, and he mixed it with hydrogen gas, and he was able to make ammonia. And so the German government, they were able to take this ammonia and they were able to make fertilizer, but they also were able to make explosives. So because of this process, this is how the German government was able to start World War I and start World War II. So looking at this famous equilibrium reaction, what are 4 ways that you could manipulate, using LeChatlier's principle, this reaction so that you make lots of ammonia? Go ahead and stop the video and then see if you can come up with the answer. 4 ways to maximize the ammonia being formed. You can increase the concentration of the reactants, the nitrogen, the hydrogen. Make sure you have abundance of that in your reaction vessel. You can remove the ammonia as it's formed. So that's why it's continually favoring the product side. You can remove the heat. If I can remove it, take towards. It will shift towards the product side. And then I can influence the pressure. I see that on my reactant side I have 4 moles, and on my product side I have 2. So if I increase the pressure, then that will favor that product side. And there actually is one more way to influence this, and that is to use a catalyst to make it faster. The catalyst doesn't change equilibrium, it just saves you time. If you're interested in seeing a YouTube video of this, there are some links there. Carl Bosch, he also looked at Fritz Haber's reaction and he just made it better. It also was the end of the natural fertilizer trade. When you look at the results of this scientific discovery, we see that there are huge population growths in the 1900s because there's more food, and so therefore there is more people. And if you go and look at your cells, we find that 1/3 of everybody's nitrogen in your body comes from this process. So this is a very important process to help generate food for the world. A side note of this is we produce too much and put too much on our farmland, and so we get nitrogen pollution. And this is the Gulf of Mexico, and dumping a whole bunch of nitrogen in water causes these algae blooms, which causes the oxygen in the water to decrease, which then causes more wildlife to die because they don't have enough oxygen. And so there needs to be a good balance, but now we're producing so much nitrogen that we're now polluting our planet. Here's just a diagram of LeChatlier's principle with the Haber process. So I mentioned in the Haber process that a catalyst just makes everything go faster. It increases the rate that equilibrium is established, but it does not influence the concentrations at equilibrium. And here is a chart that shows this. So it just shows it getting to equilibrium faster because a catalyst is used. The AP board loves to ask questions of when K can change, when the equilibrium constant can change. So adding a catalyst does not change the equilibrium constant. It does not shift the position of equilibrium. And again, it just helps you reach equilibrium sooner. Go ahead and try this problem. Stop the video and answer. So I'm going to remember add away, take towards. So on A, I am removing my water. So that means it's going to shift towards the products. And what this means is it means I have more products. In B, adding some liquid water. That's no effect. Water is a liquid. Liquids don't influence equilibrium. C, HF is removed. So this time I am removing HF. So take towards, so it's going to shift this way. So I'm going to have more reactants. And D, some sand is removed. Sand right here, silicon dioxide, that is a solid, and solids don't affect the equilibrium, so no effect.